Section 3-4 is on the definition of derivative as a function. The objective of this section, remember, is given the equation of a function, find the equation of the derivative function. And as you recall from the first half of this section, we were finding derivative functions by using the formal definition of the derivative function, which is that limit as h goes to 0 of that forward difference quotient. And then we also looked at how we can kind of speed up that process by using some of the properties. We learned the power rule property, and we also looked at the three properties for finding derivatives, in particular the property of derivative of a sum, the derivative of a constant times a function, and the derivative of just the constant function. And so I want to start out with actually one of those properties, and actually it's the derivative of a sum of functions. And as you may recall, it said if f of x is equal to g of x plus h of x, then f prime of x is equal to g prime of x plus h prime of x. So in other words, we can read that off as the in this way. We can say the derivative of a sum of functions is equal to the sum of the derivatives of the functions. Derivative of a sum is equal to the sum of the derivatives. And what I want to do with this actually is to look at the proof of how we know that this is the case. And there will be several theorems and properties throughout the year that we'll stop and look at the proof of how we know that that is in fact the case. And we'll take this, this one is a very nice one to illustrate a proof. So we're going to use simply a direct proof to show this. And we're going to start out with what the hypothesis or the conditions say here. That is that if f of x is equal to g of x plus h of x. So that's what we're going to start out with. We're going to let f of x equal g of x plus h of x. And the conclusion you can see is about the derivative of function f. So we're just going to go back to our definition of f prime of x and use it to help us prove this. So this is that formal definition that we talked about in the first half of this section. F prime of x is defined as the limit, and we defined it as the limit as h goes to 0. But because I have a function here that's called h, to avoid the confusion here, I'm going to use that other way that we wrote down the definition, and it was in terms of delta x instead of h. So I'm going to use delta x in this little proof. So it's the limit as delta x goes to 0 of f of x plus delta x instead of x plus h minus f of x all over delta x, again, instead of h there. And then the next step of this is just substitute in what f of x is equal to. So it's the limit as delta x goes to 0 of the following. I'm going to replace f of x plus delta x with what it's equal to. So I'm going to replace the x's in here with x plus delta x. I'm going to rewrite this in terms of function g and h then. So f of x plus delta x would be g of x plus delta x plus h of x plus delta x. And then subtract what f of x is. Again, that was that's what our assumption here was, that f of x was equal to the sum of these two functions, g of x plus h of x. And we're going to divide that all by delta x. Okay, so the first step is a substitution. And now the next step, I'm just going to reassociate some things that I have in the numerator there. I can see that I have a function g of x here, actually g of x plus delta x, and I have g of x over here. I'm going to put those two guys together, and I also see that I have function h here, and I have function h there. I'm just going to group those together. So this is equal to the limit as delta x goes to 0 of g of x plus delta x. And don't forget that minus sign gets distributed through to the g of x there, so it's a minus g of x. So I'm going to group those two together, associate those two. And then do the same thing for function h there, plus h of x plus delta x. And again, don't forget that minus sign gets distributed to a minus h of x there. And that's all divided by delta x. And what I want to do here is use the property of a quotient or a fraction here that allows me to split up this quotient that I have into two separate quotients. And in particular, I can rewrite it this way. The limit as delta x goes to 0. I can rewrite this as g of x plus delta x minus g of x, all divided by delta x. And then add that to h of x plus delta x minus h of x all over delta x. And we're taking the limit of this whole thing. Usually we use that property in the other direction here, that if I had these two fractions here, these two quotients that I was adding together, since they have a common denominator, I can combine those into one quotient or one fraction there. I'm just using it in the other order here though, breaking it apart into two separate fractions. And now what I have here is the limit of a sum. I've got a limit of a sum of two things. And going back to my theorems for limits, I know that if I have the limit of a sum, it's equal to the sum of the limits. So I can rewrite this way. I can rewrite this as the limit as delta x goes to 0 of g of x plus delta x minus g of x all over delta x, plus the limit as delta x goes to 0 of h of x plus delta x minus h of x all over delta x. Okay, limit of a sum is equal to the sum of the limits. And now what I can see that I have here, I've got the limit here of a difference quotient. G of x plus delta x minus g of x all over delta x. That's a forward difference quotient right there. In fact, I have another one of those guys sitting right here. This is a limit of another forward difference quotient. In fact, if you go back to what we started with in this problem, that's what I started with in the very beginning of this problem, is I have a limit of a forward difference quotient is how I defined what f prime of x is equal to. So if I have the limit of a forward difference quotient, I can replace that with the derivative of that function. And that's what I'm going to do. I'm just going to use my definition of a derivative function to replace these with what they're equal to. Again, the limit as delta x goes to 0 of this forward difference quotient for function g of x is just g prime of x. And the limit as delta x goes to 0 for this forward difference quotient for function h of x is known as h prime of x. And there is our proof. I have that f of x is what I started with over here on the left at the top, and that turned out to be equal to, on the right, g prime of x plus h prime of x. In fact, if you want to just bring down the f prime of x so you can actually see that property show up there at the very end, there in fact is the property that we're looking for, that f prime of x is equal to g prime of x plus h prime of x. That's what the theorem says at the very beginning. If f of x is equal to g of x plus h of x, then f prime of x turns out to be equal to g prime of x plus h prime of x. We have proven what we needed to prove here. And you'll see in the book there many times they're going to write QED at the end of that, which is Latin for the abbreviation for Latin quod erat demonstratum, which basically says what was meant to be demonstrated has been demonstrated. Basically, it's the conclusion to the proof. All right, you'll see several problems like that in your assignment where you'll have to prove one of those properties that you've been working with. So that's why I wanted to go through that example with you. Take a look at example 3 on page 88. It says, check the answer to example 2, which actually we did this example in the previous section, or the previous notes. But we'll just quickly show how we can use our calculator to help us verify that our derivative is correct. They gave us the function 5x to the 7th minus 11x cubed plus 12x minus 47. And they had us find what f prime of x is equal to. I'm just going to go ahead and write down what that derivative was. Remember, it was 35x to the 6th minus 33x squared plus 12 was our derivative function. And so they want us to use the calculator to verify that this is correct. It says graph both the algebraic derivative, which is what I just wrote down, as well as the numerical derivative. That's using the nderiv command on your calculator. So here's what I'm going to do on my calculator. I'll go ahead and write it on the board so you can see that. But in y1, I'm going to put my original function. That'll be f of x. In y2, and I guess it really doesn't matter which order I do these in, but I'm going to go ahead and put the numerical derivative in y2. It doesn't technically matter which way you want to do this, but I'm going to do it this way. So I'll say nderiv of y1, my variable is x, and my value is x. And then in y3, I'll put in the numerical, or the algebraic derivative I just came up with, which was f prime of x. So that's what I'm going to punch into my calculator, and we're going to see if y2 and y3 end up being the exact same curve. And according to the work that we've done, it should end up being the exact same curve. Okay? All right. So let's take y1. We'll put in the original function there. Technically, I don't need the original function to graph, but we'll use it to graph the numerical derivative. So it's 5x to the 7th minus 11x cubed plus the 12x minus 47. And in y2, let's put in nderiv of y1. My variable is x and my value is x. And then in y3, let's put in the numerical, the algebraic derivative that we came up with, 35x to the 6th minus 33x squared plus 12. And in fact, I'm going to, since I'm assuming that that's going to show up right on top of my numerical derivative, I'm hoping that it does, I'm going to change this to that little tracer. There we go. So I'll trace the path on top of the curve there. And I'm going to go ahead and shut off the original function here since I don't really need it to graph along with it. And I'm going to graph this, I think in the, well, let me change the window slightly here. I think we'll use a window similar to what the book shows us there just for ease on this one. But I'm going to go from -2 to +2 for my x's. And for my y's, I'm going to go from -5 to, I would say about 30 here should give us a decent window for this thing. Oops, and a scale of 5. And we'll graph that. So again, the first thing that we should see show up here is the numerical derivative. This is what the calculator is telling me the derivative should look like. And the next thing we should see here is our derivative function that we came up with. This is what we're claiming the derivative is. And again, we want to see that those two are right on top of each other because we want to check to see that our answer is correct. We're checking our work compared to what the calculator is saying we should get. And they were the same. Looks very nice. Okay. Let's take a look at the next example here. Oh, before we get to the next example, there's a couple of terms that we need to talk about here, and the notation that we use to describe a derivative. So the derivative notation and terminology. There are several ways that we can indicate that we are finding a derivative. And the first one that you've seen and used several times now is just f prime of x. We read that as f prime of x, or sometimes we say f prime at x. We'll use f and then a single quote, and then in parentheses we put our x. That's one way to write it. Sometimes they give you a function that's in terms of y equals something. So in those cases, instead of saying f prime of x, we would say y prime. Here's another notation that we use sometimes to write a derivative. We'll talk more about this notation later. But this is read as dy dx. We'll talk about what dy and dx actually represent in a later discussion, but this is another way that we represent a derivative. It's indicating the change in y, dy, over the change in x, dx. Remember, a derivative is a change in y over the change in x. And the last one that we can write this as here, sometimes we take that y out of the numerator when we write dy, and take the y and put it off to the side there like we have it written there. And so we would read this as d dx. That's the quotient or that fraction you see out front, d dx of y. That's how we read that. And that actually introduces us to what we call our derivative operator, that d over the dx that you see there. Again, we read that as d dx, but that right there is what we call our derivative operator. That if I ever want to ask you to find the derivative of something, there is a certain notation that we use to indicate just find the derivative of this expression, and that's the d over dx. Just like we have a notation that we use to indicate find the limit of this expression, the lim of as x goes to whatever. This is the notation we use to indicate a derivative. d dx of f of x means take the derivative of f of x. So d dx, like we saw up above there, of y means take the derivative of y and write what that's equal to. All right, so those are different ways that we write a derivative or indicate that we want to find a derivative. All right, so let's take a look at a couple more examples here. Example 4 there on page 89 says, if y is equal to 7 times x to the negative 4/5. So y is equal to 7 x to the negative 4/5. Write an equation for the derivative function dy dx. Okay, so you could write this as y prime. That'd be one way to do it. In fact, I'm going to write it that way just so you see that's the same as saying dy dx. Again, these are just notations that we use to indicate that we're finding a derivative. And so just use your derivative properties as well as your power rule here. You've got a constant times a function, so the constant stays out front, and we multiply it by the derivative of our function. And so x to the negative 4/5, that's a power function, so follow your power rule. Power rule says bring the exponent out front, the negative 4/5, and take x now and raise it to 1 less than what you had before. So negative 4/5 minus 1 would be a negative 9/5. And again, I would suggest that we combine our constants there. You could do that all in one step as you're writing it out, but we have 7 times a negative 4/5. You could write that as a negative 28 over 5, x to the negative 9/5. Or if you want to, you could simplify the negative 28 over 5. That would simplify to 5.6, a negative 5.6, x to the negative 9/5. All right. There's just seeing some of that new notation show up there, as well as using some properties we've used in the past. Let's take a look at one last example here. It says if y is equal to 7 to the 5th, then find y prime. Y is equal to 7 to the 5th, then find y prime. Now don't let this one fool you. It looks like a power function at first, perhaps because of the fact that you've got something raised to the 5th power. But remember, it's only a power function if the base has an x. It doesn't have an x here, so it's not a power function. In fact, it's just got numbers in it. This is just some constant. I don't know what x 7 to the 5th is. I could punch that in my calculator and get whatever numerical value that is. And so I have to use the property for the derivative of a constant. Derivative of a constant, remember, is always 0. And the reason for that is because the original function is just a horizontal line. Crosses the y-axis at 7 to the 5th. And so the derivative at every single point on that function is 0. It's a horizontal line. Its slope is always 0. And that is the end of the notes for this section.